Mic check. Okay. So, hello everyone. My name is Boyuan Chen. I'm currently a researcher at Huawei Canada from Center for Software Excellence. So today we are going to talk about performance. Before our talk, thanks everybody for staying for the last day. And okay, so this whole talk is going to be categorized into two parts. The first part, I'm going to give you a background of the FM inference serving and the SOTA techniques that currently happening in the industry and open source community. So this part is not so software engineering, but it could form a background or foundation that later on when we kind of present the challenges of the software performance engineering challenges for FMware as a whole. That would be covered by my colleague Jiang. Okay. So a very quick recap on the decoding. So I'm pretty sure in the past few days, like many people have been explaining this, but I just want to rephrase this so that you have a fresh memory. So for the prompt that's being put into the large language model or foundation models, and for now we just gonna zoom in into the decoder owning foundation models like GPT and Llama kind of architecture. We're not going to talk about a more kind of advanced architecture like a mixture of experts or Mamba or any of these new architectures. I'm pretty sure later on when the new architecture boom up, there are kind of new techniques. But for now, let's just stay at the decoding process for decoder-only GPT-like models. So the first thing we do is that we're going to have these tokenization. And usually, the tokenization comes with some pre-built libraries, like algorithms, for example, like a BPE, that you use a lot of the frameworks libraries to help you. But the idea is that in the top left corner of the image is that you have bunch of tokens that formulate a vocabulary size, and this vocabulary size is basically fixed throughout the life cycle. And And you will have a next step is you do an embedding, and usually you will have an embedding size. So the embedding size could be here showing from small 768 to all the way to 1,600. So for each token, it was represented as a tensor 1768. And because the transformers have a notion of the positions, that's the tokens in the sentence. So you always have positional encodings like rope or WP, these kind of encodings that you add it together. It's the same shape basically with the token, and you add it together with the embeddings you have. And the next step is you go through a bunch of decoder blocks, and you have seen the transformer architecture, and on the left side is the encoder, on the right side is the decoder. So ignore the encoder side, only focus on the decoder side. Then it's just a bunch of decoder block which contains the head, multiple heads actually. But what essentially you're trying to do is generate one token at a time. But there are two phases basically. The first phase is you just put the whole prompt into the model, and that's the yellow shaded part, which represents 3 tokens here. And then you generate token by token by the blue shaded box. And at the end, you will basically meet with the end of token, and the model knows that I can stop here. But what is the output really? Many of the times if you use a Llama or kind of the serving engines, it will just directly give you the results. But in fact, for every, basically at the end, it was just a logis we call, but it's a probability of all the tokens, which is the vocabulary size. So all of the 50,000 tokens, you will have a probability, which we call logits. And you apply kind of sampling techniques like beam search, or you can do parallel sampling and all kind of decoding strategies, sampling strategies to choose the next token that is most likely to be. So that is the kind of a quick recap on the decoding process. Okay, so attention is all you need, right? But what is really is, so we don't really need to know, for performance perspective, we don't need to know AI people, what does query mean, what does key mean, what does value mean, because they need to know these things so that they can somehow tweak the model architecture so that they can just change things to do some kind of research. But all we need to know is this formula here that essentially you have 3 matrices. And the 3 matrices coming from the token embeddings you had before. And then you do a matrix multiplication at the top, divided by some parameters, and do a softmax on that, and then do another matrix multiplication. And that's the most time-consuming part of a decoding process. And because each of the attention computation is actually happening in one of the heads, but in reality, for a very large model, you have multiple heads. So and each of the Q key is a very large matrix, so it's just going to cost you a lot of computing resources. To give you more kind of a feeling about it, so break down into shapes. At the top, you will see that a T basically represents timestamp. Here is just timestamp of 1. Consider your input prompt is just 1 token, right? And remember we say that embedding size is 768. So TC at the top, the input is a tensor of 1768, so the shape is 1768. And then your head size is probably like 16. That means actually there are 16 blocks of doing this attention computation. And every QKV is a shape that's reverse of 768 and 16. And you have to do the multiplications. And at the end, you will get an attention score, which basically looks like the same size of your the 1 token at the beginning, and then the hidden size of 16 of your head size. So that's all basically, and you can already see that there's kind of quite a lot of numbers here to be computed. So that's really brings the thing to slow. And one of the most important thing that I wanted to mention, probably many of the experts mentioned before, is KV cache. So what is KV cache? So if we go down to the computation of the attention, let's consider that when there is no KV cache at all. So at the first step, you basically have a query token. Here the embedding size is the 768 we had before, right? So remember, every Q key V is just a fully connected layer that multiplies the token that you have as the input. So let's say your first query token, and then you do a matrix multiplication to be the transform of the key, and then you get the number at the top. And then your second query token coming again, you have to compute the key basically again. You can see the green part is actually repetitive, right? And then you can get the QKT again, and then compute the results, and again and again. So whenever there's a new query token coming, you actually need to recompute the key value, key tensors and the V tensors again to basically to get the results of the QKT. And that is not very efficient, right? So what happened was naturally is like when you have the query token, so query token is always going to be different because the new token coming in, you never know what the query token is going to be represented. So there's no need, or there's no, often the question is, how can I just cache the query token? There's no need because every time it's new. But you can for sure cache the key tokens that you see before. Here is the purple part. So when the purple part you save, then you basically don't need to recompute the key and V. You save a bunch of matrix multiplication here, and go on, and then eventually that you just need to go through each query tokens and multiply by the already computed key and the new key that new key and V brought by this new token. Okay, and so we're talking about performance here. Why does it matter? So the two things. So the first thing is this is kind of like a model of I believe is a 40 gigabytes A100, and some models around like 7B or 13B. But the idea is the parameter is going to take around 65% of the memory, but the KV cache takes almost like 30%. So it's a huge block of the memory consumption. And as the batch size increases, you will have to hold more KV cache for that, and that sometimes may cause your system, out of memory, and so you have to actually control the batch size of your. You have to see how much requesting can take for that. And all these things, KV cache doesn't exist in training. The reason because training is not actually doing one request at a time. For training is actually you take, let's say, a batch size of 8 or batch size of 16 and feed into the model all together. So it doesn't really need the notion of KB cache. Instead, it needs things like, for example, the states of the optimizers, things like that. So it's completely a different performance model in here. Okay, before we basically say, introduce some of the existing serving system, I would like to first introduce some kind of model that people usually use. This is kind of a commonly used in CPU world. It's called a roofline model. So roofline model is a way to basically, simply speaking, evaluate your program to see whether it is compute bound or memory bound. What do I mean by compute bound and memory bound? So compute bound means that your speed or the performance of your application is actually being controlled by how many computations you can do per second. And usually the unit you do in deep learning world or in foundation model world is flops per second, right? You can always see, NVIDIA release a new type of hardware, and it can reach what are the top flops per second they can reach. These are basically the max, the theoretical upper limit of the computing power. And the other more important issue is how fast is your data being moved. And that is the memory bandwidth, which is calculated by bytes per second. And you divided these two metrics, get a concept called operational intensity. Basically, then for every your program, you can actually profile your application and put it into, like the application can be some dot inside this axis on the right side. But the idea is basically saying that if you're at if your dot is, can I do this? Oh yeah. So if your dot is under this area, then it's like a memory bound. Then if your dot is at this area, then it's compute bound. What essentially means, straightforward way is to say that if your engine is so fast that the fuel cannot really, feed enough fuel for it, so you can still, your compute resource is still idle. But on the other hand, if you just keep feeding them fuel, but your engine is so slow, then you cannot go fast as well. So that is basically the model to see how the computation is modeled in the inference kind of set thing. But it can be used. It's not just used in when we were studying the model inference. It actually can be used for many of the other applications as well in the CPU world. Okay, and then the reason I brought up is want to introduce you about this technique called flash attention. Flash attention is something that was brought up in the early 2022, yeah. And then later on evolved to version 2, version 3. So this is basically integrated into many of your serving engine if you ever try to serve your local model. Basically, the rule of thumb is like if you don't know you're using it, you're basically using it because the kernel is integrated in almost every inference engine nowadays. So it's real. The left side is basically reflects what I just mentioned. You have basically formulates a very simple program model. A very simple performance model is you have 3 layers of data storage, right? The bottom layer, which contains the most DRAM, which is your CPU DRAM. So usually you will see like you get a computer, the CPU RAM is like 32 gigabytes, 64 gigabytes, whatever. And then the speed you can see is very slow, right? Compared to actually the GPU HBM, which is I think short for high bandwidth memory. So the GPU HBM is actually the specification we'll get from the advertisement. So A100 has 40 gigabytes of HBM, H100 get 80 gigabytes of memory. So that's the part in the green zone. But on top of that, there's SRAM, which is even faster for data movement, but it's extremely small. Like you can see that it's only like 20 megabytes, but every computation happened, the GPU needs to actually take data from there. So you can almost consider it like a cache, level 1 cache, level 2 cache, level 3, etc., something like that. You don't need to know all the details of flash attention, but there's a paper there. There's tons of tutorials, documentation about there. But the rough idea is that when you were computing the attention, we already showed that there are many operations that you do for the attention. One of the challenges that the softmax computation actually needs to take all the data in one vector, so that every time you are doing this computation, you have to move data into the SRAM. But it is extremely time consuming if you're not doing this well. So what they do is they fuse this whole 5 operations into one kernel, so that it lets the data that they need to compute to stay in the SRAM as long as they could, so that they don't need to basically be concerned with the overhead that's being caused by the data movement. And under the hood is a bunch of, it's coming from an idea called online softmax, which you can basically cut the softmax into pieces and then move them to do the computation, so to formulate a pipeline, so that eventually you can tell the matrix computation and make it more efficient. But that doesn't matter. Like, all I wanted to show in here is just to remind you that in the model inference or the FM service, data movement is actually a very, very important topic that right now people are trying to solve, even for the size of the model, right? We all know that the model size is very, very large these days. And consider if you're trying to serve a serverless model service, and one of the important things is, like, whenever there is a new model coming in, you have to actually realize it's not like the traditional serverless functions, you can immediately get it. And even for traditional serverless functions, you have this cold start latencies. But for model, it's a different thing. Like, if you load the model, even down, like if you try to download it from S3 buckets and load it, then it's going to take basically forever. That's will impact your online service performance. Okay. So enough with the low-level stuff of decoding and attention. This is not trying to say that give you a very detailed walkthrough of how they were computed, but more like take you to the world of FM inference as well as FMware performance challenges. So on the left side, we basically summarize there's 3 different type of task heterogeneity. So these applies to almost all of the workloads that we can see, right? So on the left side is the prompt. So you would probably have a very long prompt, but then your output is very low. So that basically means your decoding process is kind of that doesn't need that time, but you actually fill in a very long prompt into the what's that thing called, into the GPU. And this is usually, like, for example, you're trying to summarize the documentation or some other task like that. And sometimes you can also give a specification of very short descriptions, right? For example, generate me some algorithm to do something, but then it will give you a super long response. I'm sure you will have all these experience when you try to ask ChatGPT to do some coding for you. They generate a very, very long code, and then that means that basically the prompt fitting in is very kind of short, and then the generated output is very, very long. And there's another scenario which is most probably performance consuming, is like you have a very long prompt and the generate is a very long prompt. So that's kind of like, for example, I could think of like a refactoring, or maybe other scenarios you also have this. And for these different task heterogeneities, the performance requirements are sometimes also different, right? Sometimes you probably care more about the time to generate the first token. As long as the first token is generated, you don't really care about how much, how fast the tokens can be generated. As long as you can, keep it to pace, that you can read it in a human kind of way, like, for example, 10 tokens per second or 20 tokens per second, that is enough. But think about it, if this large language model or foundation model is in the middle of your pipeline, right? And the downstream pipeline actually needs the results for in the middle, and it actually needs to wait for all the tokens to be generated so that it can get it. And in this time, the overall latency actually matters. So that's just some examples just to show that the requirements of latency can be different, and sometimes it depends on whether you are doing online services or you're doing offline services. The requirements are also different when you have like latency and also the throughput. Okay, so that's the heterogeneity of task part. And on the right part, which is the non-determinism, and we all know this. So the number of tokens that's being generated is uncertain. It's non-deterministic. And if you know that why we're talking about KV cache before is actually you need to allocate the memories for storing this KV cache, right? But if your generated token length is non-deterministic, you don't know how much memory you're going to generate. And what do people do? Usually is that they, like in the alpha age, like in the 0.5, 0.6 age, that's not formal. Like right now we see a lot of inference engine, but at the beginning people just assign a larger chunk of memory, so that these chunk of memory can hold all of the reserved KV cache. But you can already imagine that it's very waste of the memory resource. So this is something that we have to consider, because the more memory you waste, basically means that the fewer prompts you can process at the same time. That means lower performance. Okay, and these basically summarize a few challenges, open challenges that people are trying to solve today. So okay, so if you really try to serve FM, not just serve for example, for prototype, for sometimes you give them a prompt, but actually serve a foundation model for a large group of people. Traditionally, if you do like a web backend, you will see some common, very similar concept here. You need a load balancer, right? You need a scheduling. You need to decide the number of replicas of the FMs. You actually need to know when can I scale up the replicas of the model? When should I scale down one of the models? And how do I dispatch the inference request to this replica or to that replica? So this is something that you need to decide. And to decide that, you need some kind of references. Like how do you decide that? It's usually based on service level agreement. And this part is going to be a very important part later on in Haoxiang's talk, that we're trying to make the application level SLA to be guaranteed. But essentially, these performance requirements give you some open challenges. The first is like how do you design a load balancing techniques, and how do you basically design the request priorities, and again, how do you avoid memory waste, and what are your scaling strategies? I'm going to touch a few of them by introducing some existing popular work. Okay, so the first one is published, I think, last year in OSDI, which is called vllm. I'm pretty sure many of you have heard it, or maybe just use it. So one of the most important concepts we mentioned is paged attention. So remember that we say that KV cache is important, is you need to manage. So the motivation is like, if you don't manage it, then just like this. So you generate these prompts, and then there are 2 generated tokens. But your request, your context length, the sequence length, you usually see in the Hugging Face model, they have a description, right? So like 2048, 4096. These are the context lengths as much as they can go. So you will basically reserve all of these tokens for that, and it will be basically what we call the internal fragmentation if you actually pre-allocate a huge chunk of resources. And if your GPU is having to do multiple requests, then there will also be external fragmentation, because 2 different requests might have the different sequence lengths, so you're trying to kind of manipulate through that. So that's the issue people are trying to deal with, so pretty straightforward, right? So what the idea is basically like the traditional operating systems. So we have a mapping table and virtual blocks for storing the KV cache. Instead of just trying to allocate it in a static way, just everything static assigned beforehand. What this paper do is basically have some logical KV blocks, and you have a block table just like a reference, and every time it only assigned a certain memory size, where here they call it block, which usually here is basically say each block takes only 4 tokens at a time, right? So in this way, the model is actually, the tokens are actually allocated on demand, so that avoid some of the memory loss, waste. And if you have more requests, same thing, that you can have, for each request you have a block table, and then for each request you can store this in a more kind of packed way of the memory. Okay, and more benefits. So one of the sampling techniques is called parallel sampling, and this I believe has been used in Copilot and many of the coding assistant chatbot, is that you have the same prompt, but when you fit into the FM, it will basically give you multiple outputs. so that you can choose between these among these multiple outputs, so that decide which one should I use. If you don't have, like, for example, a page attention or this kind of KV cache management, then you're probably going to have a redundancy of your prompt, the cache in the memory. So in this case, like, you probably have 3 different copies of that, right? But by doing kind of like this kind of reuse of the KV cache, then this part of the memory is also saved. And also, it can also be used like for beam search when the beam is not branched. Then the memory can also be reused. So a lot of benefits, but most important thing to take away is this attention technique is trying to manage your KV cache more efficiently. So eventually you can, when you serve a foundation model, more and more requests can be served at the same time because you save more memory, right? Originally, you probably can serve only 2 requests at the same time, but now you can serve 4. And the throughput is just increased. Okay, and another important concept, or I wanted to mention, is on the decoding process. So previously, we were basically focused on the managing of the KV cache, but actually for decoding, there's some very popular techniques called speculative decoding. And this is a little bit similar. I believe this is, I think my colleague Kirill talked about like layering of the different small models and large models. So you can use the small models to simulate the large models' behavior. And this here, speculative decoding, is the same idea. So the observation is that it is not always difficult to predict the next token, right? Look at the 2 examples here, like the city of New, most likely you will say city of New York. And the other example, this means that. And this next token is more like harder to predict than the one at above. So the idea is also very straightforward and very simple. So you just use small models to predict the easier token, right? Then you could save much of your time. Although small tokens need to do token by token, as well, but it is actually much faster than the large model. Sorry. So the 7B model is actually faster than 70B, like almost 10 times, like 9 milliseconds to generate a token compared with the 90 milliseconds. But very straightforward question is, how do you know which token is easier? And then you need some algorithm. So what we have is 2 models, a draft model and target model. So the draft model were basically the small models, and the target model is the big models. So basically the idea is I use let's say each time we do this decoding, we do it 5 steps, right? So I just use the small model to generate 5 tokens, 1 by 1 as well. So each token that I can have a probability. Remember the lodges we mentioned before? So that is the probability that you have in here, like dogs love chasing after cars. Every token's probability is here. So you're doing this, right? And then you use so basically that's here. You draft a model for k steps. And then you run target model once. Why do I only need to run once? Because you can actually have all these tokens piled up together and formulate a batch and send to the target model as a one inference. Because you already know kind of like first time you can have the dog in your prompt. Next time you have dogs love in your prompt. Next time you can have dogs love chasing at your prompt. It is almost like you're doing a training. And because doing training kind of thing and doing inference is very different. Inference you do 1 step at a time. So run your target model once actually doesn't really cost that much compared to running it 5 times. So what ends up with, because you run it as a batch, but even you run it as a batch, every time you will also get a probability from the one run of the target model. Then the easiest part comes in. If your small model's probability is smaller, fewer than the target model's probability, that means both of the model believe, and the large model even believe this word is even stronger, just like this case, right? So basically the large model, the target model believe this is even more, the probability-wise is even more than the small model prediction. So that means you can take the token. And again, next you can take this token, and next you can have this, but then this is when you actually accept it with a probability. So it's not like a reject right away, but basically you're trying to decide with a probability to whether I should take this word. So yeah, so this is the, and you can already tell like by doing this, if there's a lot of words, a lot of tokens already be generated by the draft model, then you can already use it. So speculative decoding is also a common technique that is being integrated in basically all of the inference engines that you know today. And the next thing I'm going to introduce is coming to a more kind of, because the whole kind of thing I want to do is from the bottom, like to be the decoding and the attention, and then one FM service. And right now we're looking into multiple FM service. So right now, this is also one of the most popular techniques that you're is using in online serving. It's called continuous batch. Again, motivation. Why do we need that? The first thing is you may consider doing batching, right? But because the generated token length is very different, so if you're doing static batching like the left side, what you're gonna see is like each of the prompt, when they generate tokens, the sequence length is very different. So this one is generated all the way to the end of the time sequence. But these ones, and the first one, they already finished before that. That means that they create a bubble in the computation. You're wasting resources. You're wasting computing power. Basically, you're wasting money, right? That is not good. So we're going to improve that. How? Basically, every time, if you generate, if you see, this is kind of like your plane, right? You're driving, you kind of like have 4 car rows at plane. You can only take 4 because the more you take, the more memory you consume. The more memory you consume, the more easily you hit a OM. Here, every time when you finish, you just immediately get another sequence to come in. So, for example, right now, like when they were end, then the S5 here, S7 here, S6 here to actually continuously executing. So by doing this, you basically keep the GPU always busy. Although there are some technical details about, for example, when they were doing S6, you may wonder like, oh, when I was doing this, isn't this like a feeding in all the prompt into it, but not actually doing decoding one token at a time? Yes. So that's why at this time that you actually have to wait. So you have to actually wait for that prompt to be finished and before moving on. That's kind of like a cost you have to take. That also will kind of impact the latency of your actually other inference. So that means that you cannot get a best latency and best throughput at the same time. So that's always a balance over there. And that's actually some design decisions you have to make when you are trying to develop a software like this. Okay, and the last part I want to take is after batch. A batch is like one model takes in multiple prompts. Then the more thing is like, how do you serve multiple models? How do you serve multiple replicas? And how do you serve all these kind of things? So many models at the same time. You might also have the experience that you need to fine-tune model for this, fine-tune model for that. And in the future, we believe FMware is like model is just one component of it, right? You need many, many models to do it, but not all of the resources can do that. So instead of trying to burn as much as GPU and cause your wallet to be empty, what you can do is actually use the limited resource to serve these models. Back in the deep learning age, this is the project proposed by IBM. It's called K-serve model mesh. So what essentially we're trying to do is to create all these pods, but you put models in these pods. But you do it kind of like an LRU kind of thing, right? Because each time you can only serve one model due to the memory constraint. So this time you're probably just serving A, and next time because A is no longer needed, so you swap the model to B, C. So these are some things that you can actually, some interesting work are going on right now to kind of manage the multiple replicas of the model more efficiently. Some representative systems like IBM, there's a model mesh, there's fast swap proposed by Alibaba. And if you know, like I believe we talk about LoRa models as well. There's also one paper talking about how to use one GPU to serve thousands of LoRa's. That's also basically the similar thing, right? You have to swap the adapters based on what have been used more frequently. And the idea is like model loading is extremely time consuming. Even in deep learning age where you only have millions of parameters, now you have billions of parameters, so you want to keep your model always hot. to avoid the loading time. That's something that you have to consider when you trying to either benchmark or trying to design a more kind of performant solution. So yeah, that will be all from my side. And next, my colleague will introduce a more interesting part about how do you actually connect all the dots from a single FM like model-based view to a application point of view, which is the next section. Thank you.